Welcome everyone to this series of lectures on the naive Bayes algorithm. In part 1, we're really just covering Bayes' theorem, not naive Bayes. So to be clear here, naive Bayes is the shorthand for a set of algorithms that use Bayes' theorem for supervised learning classification tasks. Now Bayes' theorem is a probability formula that leverages previously known probabilities to define the probability of related events occurring. So let's actually dive deeper into this idea of just discussing Bayes' theorem. In part 2, we'll discuss the naive Bayes algorithm for machine learning. So, as I keep mentioning, naive Bayes methods are just a set of supervised learning algorithms, and they're based on applying Bayes' theorem, which is shown here. And a little bit of history of naive Bayes and Bayes' theorem is in the 1700s, Thomas Bayes was a Presbyterian minister in England who studied theology, statistics, and logic. And eventually, he came up with the Bayes theorem shown here, which is a probability formula. And we should note that there is actually no official known sketch or portrait of Thomas Bayes, and this particular portrait is just from a statistics book from the 1930s, and it's not really actually known if this is actually him or even a likeness to him. We should also note that Bayes' theorem, the one he's most famous for, was actually published after his death. Richard Price edited and published his notes that included his famous theorem shown here. So let's actually now walk through Bayes' theorem and what it actually represents. So Bayes' theorem basically says the following. The probability of A happening given B is true is equal to the probability of B happening given A is true multiplied by the probability of A happening divided by the probability of B happening. So if we just break this down into separate components, A and B are events. So we can think of A event happening and then B event happening. And then we have the probability of the relation of the two, essentially saying what's the probability that A occurs given that B has occurred or happens to be true. And keep in mind here, A and B have to be different events. Then probability of B of A basically says, what's the probability of event B happening given that A is true? And then probability of A is just saying probability of A occurring, P of B or probability of B is just the probability of B occurring. So if you've never seen this sort of notation of probability and then this A bar B, essentially all it's saying is what's the probability of that first letter event happening given that the second event is true or has already occurred. Let's walk through a quick example to really clarify these ideas. And we're going to take essentially a simple word problem and convert it to something we can use for Bayes' theorem. So let's imagine the following situation for a city. We have a city and every apartment in a building is fit with a fire alarm detection system. However, they're not very good fire alarms. So there are false alarms where smoke is detected, but there's not really a dangerous fire to put out. For instance, there's smoke coming from an oven, which is expected because just something was cooking in the oven, but the fire alarm goes off anyways. And we want to know, basically, what's the actual probability of there being a dangerous fire if the smoke alarm does go off. And luckily for us, we did note down some probabilities based off history. And so we have the associated probabilities, and these are basically the three key components that we're going to be able to convert into probability events and plug into Bayes' theorem. So the first associated probability is that we know actual dangerous fires occur only 1% of the time. And the smoke alarms are not actually very good, and they go off about 10% of the time. And when there is an actual dangerous fire, 95% of those times the smoke alarms go off. So probably the key one to note here is that last one. When there actually is a dangerous fire, 95% of the time the smoke alarms go off, which technically means that when there actually is a dangerous fire, 5% of the times the smoke alarms do not go off for some reason. Okay, so now we have a question to answer. If we receive a smoke alarm detecting a fire, essentially the smoke alarm has said, hey, I've gone off and I'm detecting smoke. What's the actual probability that there is actually a dangerous fire given the three facts that we know here? We know actual dangerous fires only occur 1% of the time. We also know smoke alarms are not very good and go off about 10% of the time. And when there is an actual dangerous fire, 95% of those times the smoke alarms do go off. So if we actually do get that smoke alarm detecting something, what's the probability that it's correct and there actually is a dangerous fire? So in terms of probability events, we're going to say event A is that there's a dangerous fire. Event B is that the smoke alarm has been triggered. So then when we think about probability of A given B, it's what's the probability of a fire given that a smoke alarm has gone off? And then probability of B given A is what's the probability of the smoke alarm going off given a dangerous fire. Now take a note of these key probabilities. Probability of A given B, we're saying what's the probability that we actually have a dangerous fire given that we've had a smoke alarm detect something. Probability of B given A is what's the probability of the smoke alarm going off given the fact that there is actually a dangerous fire. And if we think back to the question we're trying to answer is, if you actually get that smoke alarm detecting something, what's the probability that there actually is a dangerous fire? And if we take a look at these two probability events, really what we're talking about is this one. Probability of A given B corresponds to the question we're trying to answer. If we know that a smoke alarm has gone off, what is the probability that there actually is a dangerous fire given what we know about these smoke alarms? And recall that we can actually turn those 3 points into probability events. So we mentioned that actual dangerous fires occur only 1% of the time. So the probability of there being a fire at all is just 1 over 100. We also know that smoke alarms are not good, and they go off about 10% of the time. So the probability of there being smoke in this particular event is 1 over 10. And when there actually is a dangerous fire, 95% of the time the smoke alarms go off. And note how we can write this probability. Probability of smoke, given the fact that there is a dangerous fire, is 95 out of 100. So we can take these and then use Bayes' theorem to figure out what's the probability that there actually is a dangerous fire, given the fact that the smoke alarm has gone off. And that's going to be equal to the probability of there being smoke alarms going off if there is a dangerous fire, times the probability of there being a fire divided by the probability of smoke being detected. And if we plug in these numbers here, we end up getting the fact that if we do have a smoke alarm going off, then the probability of there actually being a dangerous fire is 9.5%. And you can plug in the numbers yourself to check it out. And you can easily explore many other online examples by just a quick Google search of Bayes' theorem examples or checking out the Wikipedia page on Bayes' theorem. The main things you should come away with here is the fact that you can use these probability events in order to figure out the probability of event A happening given that B is true. So what we're going to do now is move on to part 2, where we begin to explore how Bayes' theorem can be extended to perform classification through naive Bayes. And specifically, we're going to be focusing on using Bayes' theorem for natural language processing classification. So when we walk through how naive Bayes works, we'll be working with the idea of actually counting out the frequency of words within document classes. I'll see you at the next lecture.